this time we're determining I of t for t greater than 0 for this particular RC circuit, which means that we'll find v of t first and then take the derivative to find I of t. We'll assume the switch had been open for a long time prior to t equals 0. So once again, we just want to keep in mind that v of t equals vc at infinity plus vc at 0 minus vc at infinity times e to the minus 1 over tau times t. So once again, we need to find vc of 0, vc at infinity, and tau. So to find vc at 0, we're going to draw what the circuit looks like at 0 minus. So before the switch was closed. So before the switch was closed, it looks like this. Current is the current going through resistor 3 over here. Let's see, resistor 3 is 4 kilo ohms, resistor 2 is 2 kilo ohms, and resistor 1 is 2 kilo ohms. And we want to find the voltage across this capacitor at time t equals 0. Well, we can do that using voltage division because we can treat these two resistors, the 2 kilo ohm and the 4 kilo ohm right here, those are in series, so we can treat those like one 6 kilo ohm resistor. This voltage is 16 volts. And so the voltage across these two right here, the voltage across those two right there, is going to be the same as the voltage across our capacitor because they're in parallel. And so VC of 0 minus, which equals VC of 0, because it cannot change instantaneously, is going to equal our total voltage times our resistance that we're looking at, the resistance that we want the voltage over, which is 6 kilo ohms, over the total resistance, which is 8 kilo ohms, which I have down is 12 volts. So that's V of 0 minus. Okay, so now let's look at V at infinity. So at infinity, we will have closed this switch up here. And when we do that, what does that do to this resistor right here? Yeah, I think I heard you right. Yeah. So it shorts it out. So it's not if we can pretend like it's not even there. But once again, so really this is the same. It kind of looks funny here, but this is the same as if we had it looking like this. Drawing it a little differently. So we can once again just use voltage division. This one is 2 and this one is 4. So the voltage across the capacitor will be the same as the voltage across the 4 kilo ohm resistor. So VC at infinity is going to be our total voltage, which is 16, times 4K over the sum of the resistances, which is 6K, which I get to be 10.667 volts. So we have VC of 0, we have VC at infinity. Next we need to get tau. So I'm going to draw the circuit as it looks during the time that we're interested in, which is very similar to what I have here at infinity. So now I actually have my capacitor there. And to get my equivalent resistance, I'm going to short out my voltage sources. And when I do that, I can see, it might be a little easier to see if I draw it like this. I can see that from the point of view of my capacitor, the two resistors are in parallel. So this one was a 2 kilo ohm resistor, and this one was a 4 kilo ohm resistor. So our equivalent is 2 kilo ohms in parallel with 4 kilo ohms. And we'll do that with product over sum. So that's 2K times 4K over 6K. So one of my K's cancels. And I have 8K over 6, which is 1.333K ohms. So that means my time constant, which is RC, is 1.333 times 10 to the third times my capacitance, which was 25 microfarads. So 25 times 10 to the negative 6. And I get that to be something that doesn't match. I have to restart my computer soon. Okay, I can't get it on this calculator. Did somebody do it for me and tell me what you got?
3.33 times 10 to the negative fifth.
Times 10 to the what?
Negative fifth.
Negative fifth. And now can you tell me what 1 over that is? $30. Okay, I did have that right. I just didn't have tau right. Okay, so now we have all that we need for writing our voltage. So V of t equals VC at infinity, which was 10.67, plus VC at 0, which was 12, minus VC at infinity, which was 10.67, e to the minus 30t, and then we needed I. Oh, okay, what did I do here? Oh, I just added. Okay, so 10.67 plus 12 minus 10.67, 1.33 e to the minus 30t. And then we want the current and it looks like I just decided to skip a step for fun. Oh, no, I didn't. Okay, so V equals IR. So we have a circuit right here. Yeah, so we don't have to take the derivative. We can just use yeah, especially because, so I wish I could go back to the beginning of the recording and change that, but especially because we are looking for the current through this 4 ohm resistor. We're not looking for the current through the capacitor at all. And during this time, the capacitor is the only thing that's providing any voltage to our circuit. So our capacitor during this time period is our voltage source. So this is V. So V is 10.67 plus 1.33 e to the minus 30t. And that equals I, which is what we're looking for, times the resistance, which was 1.333 times 10 to the third ohms. And then if you divide through by 1.33, you get 0.002667 plus 0.0003 e to the negative 30t amps. But that doesn't look very nice, so let's make it milliamps. So multiply everything by 1,000. 2.67 plus 3, probably 0.3. No, 0.33. 0.33 e to the minus 30t milliamps. Okay, so any questions on that? Okay, I'm going to save